dexterity. So we are recording. And hello and welcome to Exam 1 review session. For some of you, maybe you're not having exams this week. That's fine. We'll make sure that we cover some path and polar coordinates. I also take any kind of requests for any type of problem. So, but before we begin, let me take a little tour of what has taken place so far and what will appear on Exam 1. It'll cover stuff on Chapter 11. So what we started off with was fundamental kinematics, and those are the kind of things where we have taken the derivatives, but also taken the integrals of just those fundamental kinematic relations. Another problem, based off of that is projectile motion, which is really a special case of the constant acceleration in the y direction and a constant velocity in the x direction. We also do relative motion problems. Usually, we could also want to be able to have the skill set of drawing vector triangles with those. Constrained or dependent motion, and that's basically pulley problems. And then we did stuff in rectangular coordinates, which the i's and the j's. We did stuff, we did a coordinate transformation. We want to make sure we're able to do that. And go to path coordinates, and those are where we have the e sub t and the e sub n, right? We had the tangential and normal path coordinates. And then we had polar coordinates, which are r and er and e theta. We could call that radial and transverse, right? So those are the kind of the types of problems and the types of topics that we've covered. And here's where they are on the equation sheet. For my class, I give out an equation sheet. I'm not sure.
Dr. Deal, I don't think we can see anything. I'm not sure if you're trying to screen share.
I apologize. I totally spaced. Okay, so let me go back. Thank you so much, and I apologize. I really hate this remote stuff, and I'm out of practice. Yeah, thank you. Let's see. Is it going to share it? Is it sharing it? Whew, there you go. Thank you so much. I will restart again. All right, so there you go. Yes. Review session for Exam 1. Reset. So the big topics, the fundamental kinematics, as we mentioned, projectile motion, constant acceleration problems, or constant velocity too, relative motion, constrained motion, which are the pulley problems, rectangular coordinates, which is the i's and j's, coordinate transformations so that we could get into different coordinates, including the path coordinates, which was the tangential and the normal, e sub t and e sub n, and then polar coordinates, which was also called transverse, radial and transverse. And here is your equation sheet, and the information, the only information, at least in my class, that you'll have available to you. If you haven't already, I would print out a copy. I will give you a copy. You don't have to bring a copy yourself. It'll be stapled to the back of the exam, and when you come in, you can just rip that off the back, a free page, and you don't have to turn it in, by the way. And anyway, these are like the main equations we're dealing with. There's really not that many of them. You could actually probably memorize them, but you don't have to because they're right here. But we don't want to go through the mindset of equation hunting. We just want to use these concepts and be familiar with them. And the equation sheet is really just there as a backstop if you really just go blank. On my Blackboard, I've included these suggested textbook problems. So in addition to the practice problems I've made available from old Coast Guard exams, here's some more problems if you want to challenge yourself, and they do have the answer in the back of the book. You could pick some other ones too. So I'm willing to work through some of these. I'm not sure if the other instructors have used them as homework. These are just in case you're not familiar with the ones, because these are just numbers to you right here, but you see it from these different classes. Here's the fundamental kinematics relations. These are 3 problems that are in the book that I think we assigned them as homework or ones like them a couple years ago. Here's some dependent motion problems and constant acceleration dependent motion problems. So these are ones we could go over as well. Here's some rectangular coordinates with projectile motion and relative motion. So we could, these are also things that maybe I'm suggesting you could go over. Here's a tangential and normal coordinates. So, the path coordinates ones, there's 3 problems. I picked out and said, I think these are ones that you might run across or you might want to be able to solve. And then lastly, radial and transverse coordinates. One last thing, I also have examples that we might want to consider using. These are the ones that are posted on the recitation website. So here are examples. These are a Hibbler. Here's a path coordinates example, a coordinate transformation example, another, a polar coordinates, and another polar coordinates, and another polar coordinates. Okay, so that's the menu for today. That's a lot of information. Just threw it right there at you. But I wanted to, kickstart this off with like your options. What do you want to do? Would anybody have a request? You can put it in chat or you can speak up.
I have a quick question.
Okay, cool.
For the coordinate transformation, would we have to use ever a path coordinates and polar coordinates in an example, or could it be
I
separated?
do have an example where I went. I got to double check. I think maybe I never. The only example where I was kind of putting them together. I did them in stages. There was a more complicated one. Other times where you would need to use them there, the path would be aligned with the X and the Y in some fashion, right? So it's not, I wouldn't try to make you do a complicated angle that would like, get you all turned around and upside down, if that's an answer to your question.
Yes, it is.
Okay, all right. Yeah, I'm not looking, I'm not, and I think I've said this before, but I'll repeat it. Your goal is to make a high grade. My goal is not the opposite of that, right? I'm not trying to trick you. I'm just trying to draw things out. So here's an example right here in the center. This problem gets asked a lot of times as homework. I wish I could find more, but it's a kind of a neat one where you got the airplanes taking a dive, right? So in this one, so because the airplane is making an arc and a curve, this is you could find the acceleration of this in path coordinates, right? But that path coordinates, the normal direction is aligned with the y, right? So the tangential is, I think you can see my mouse, is aligned this way. So really, even though it's path and path coordinates, it's really kind of the tangential is the same as the x, and the path is the same as the y. So yes, you'd be doing between path and polar to be able to do this. So you do the coordinate transformation, but the path is aligned, so not too terrible. So anybody have a request? It would be bold. Say, this is what I want. We also have these problems right here that are available. These are practice problems. Got some projectile motion. So 3 projectile motion. I think 3 fundamental kinematics. So there's a 4th fundamental kinematics. Here's a polar. This actually looks like the same one. I call this one path though. Yeah. Let's see. I heard a bloop. Let's see what the bloop said in the chat. Bloop. A challenging pulley question. Okay, so we have our first one with multiple lengths of rope. Ooh, okay. Well, my ability to think on the fly or to just invent a problem ain't so great. Let me see if there's one in here that's already, or you could name one out of the book if you happen to have the book with you. Let's see. This one is one that has that those features. I think it's correct. Let me see. I heard more bloops. So more than one length equation. Okay.
I think that one you had looks okay.
What's that?
I think that one that you had pulled up looks all right.
Okay, let's do this one right here.
All right.
All right. So I'm gonna write some of this down, and then I'll switch over to my camera. So kind of draw the thing out a little bit, and I think that would be a good idea if you would do that too as we're coming along, right? So you could just, what I'm doing right now is making a quick sketch, doesn't have to be beautiful, of the situation. And you want to manage your time well on an exam, but I think there's some benefit sometimes to redrawing the thing out, especially depending on how your professor has presented the problem. Sometimes maybe there's not, you don't feel like there's enough room to like make all the things that you want. So you might want to make it like a bigger diagram or what have you. But I think the act of drawing this, at least for me, but that's a lot because I like to draw, so that's, you know, some of my preference is while I'm drawing the thing out and taking that time to do it, I'm also kind of thinking my way through the problem. And also I tend to do that while I'm practicing. So it's just like in sports, you want to practice like you intend to play, right? You want to try to you know, simulate the exam, but you want to kind of like do things that are going to keep you in your comfort zone. And also you want to try to uh, do things that are going to give you the most chance to exercise that aha muscle and trigger that aha muscle. So I'm writing while I'm doing this, right? So movers are lifting a piano, B, into an apartment. They stop to rest, but lose their grip and let go of ropes A and C, and the piano begins to free falls under gravity. So free fall is an indication generally that you know the acceleration of gravity, right? Um, when we get to kinetics, noteworthy, um, most of the time when things fall, there's a pulley problem, they don't move they're not, it's not a free fall, right? The acceleration is something less than gravity, but in this case they're saying it's gravity. So we know that G, and it appears that this is going to be in feet. So remember that G is 32.2 feet per second squared. So you might want to memorize that and not get it confused with meters per second squared, which is 9.81. And if you don't remember, ask your professor. And I'm pretty sure most people, most professors don't, you know, will if you totally like blank and like I can't remember which is which or which one is, just ask. Um, so let's see. What is the first thing we want to have to find? And we want to find
We can't
the
see what you're
oh
writing.
oh you can't see what I'm writing, right?
Yeah.
Yeah, you no, I recognize that you can't see what I'm writing yet,
Oh, okay.
because I'm still looking at I have two screens, but I didn't want to like move this one over to the other screen.
Okay.
But
All right.
wait, I could do this. I could do this. So I'm sorry. Yeah, so I was telling you while I was doing that, you should do it too. But here you go. I can move this over to right here. Yep. Okay, I can see it now. Because I needed to see what the okay, the parameters and stuff. So let me get my align this here. Move that mouse over there. Okay. So I'm hitting my so I redrew the thing out, which is my process. And my find, I want to find the acceleration of the end of the rope at A and C. All right. And then B, if initially, if there's 300 feet of rope between A and the first pulley, right? So they're talking about that distance right there, which I'm gonna call XA, and maybe they're gonna say originally. So I'm gonna write down that way. 30 feet of rope between there. What is the velocity of A at the instant it reaches the pulley? All right, so at XA equals 0, we want to find the velocity of A, and then C, which I started to make into a D. What is the relative velocity of C with respect to B at t equals 1 second? Okay, so lots of things. So the very first place to start. So making this diagram right here, or you could write on top of the diagram that already exists. I make a datum, and I'm going to make the datum across the whole thing right there. And downwards is going to be positive, but that's totally fine for now. Like later on, when we get to the final answer, don't make down positive, right? Like do a reset and answer. And it's better to answer with an arrow than positive and negative anyway. So right here, I'm going to call this, I decided to call it SA. I don't like to use X because it's a vertical thing, but anyway. Okay, so that's going to be SA. Now, I'm going to draw another datum, and I think I have this correct. Right now, another datum like that right there. And that's going to be my SB down to this location. I called it a datum, but it's really just a line. This is really the datum because it's the reference point. This is just a line. And then lastly, I'll call this SC from here down to there. So I start to get my ropes, try to figure out how much rope I have. For this first cable, length 1, we have SA plus SB. And that's all we have, right? Just that one and that one. And maybe I'll make right to there. Remember that we don't care about this. We don't care about those guys. We don't care about this thing, right? All we really care about is the things that are going to change size. And this part will change size. That part will change size. All those things will change size. So those are the ones. All the rest of the stuff can be just lumped in with the length. So my second equation here is going to be this cable. And I can see there's 1, 2, 3 SBs, and then this length SC. And if I did that too quickly, stop me and ask me, inquire, how did I know how to do that?
I have a question actually.
Okay.
You said there's 3 SBs. What about the farthest connection that's on, like the first connection to B? Is that not
This guy
also?
right here?
Yeah.
That's part of this cable.
Oh, so we just. Oh, okay, I got it. Okay.
Good. I like that noise, by the way. That's my favorite noise.
I have a question as well. Is SA and SC, are those considered the same lengths, or is that just like the way your drawing is set up?
It's
They
just the way
look
the draw is. And actually, this was a little weird because they went ahead and they actually gave you a length of the cable. Most of the time we don't care about the length of the cable because we take the derivative of these, right?
Right.
So we say, I'll just write it right here. We'll just rewrite this thing out and say equals VA plus VB. And then, by the way, we say that VA is now equal to negative VB. And then also say that this one, 3 VB plus VC, right? So now we know that VC is equal to negative 3 VB. And take another derivative.
Well.
Okay.
Why do we not consider the length of rope underneath the L2, underneath SB, like the part that connects to B?
This part right here?
Yeah, that piece.
Well, I mean, I would make it just because it's sort of a little bit. This is just a convenient line to draw from, like right to there, so I can use it for all of these. But also, just as a practical thing, you would never be able to make this thing go up high enough where this would get shorter, right? It's going to bump up to the thing. You could actually redraw this as high as it could possibly go.
Okay.
Does that
Thank
make
you.
sense?
Yeah, that makes sense.
So we have is there any more questions? By the way, don't let me
I had a
leave you
question.
behind.
So once you take the derivative of your lines, why did you, like, what made you choose variable like A is equal to negative B and like VC is equal to negative 3B? Like, why, what instinct did you have to have that relationship?
Up here or down here?
Right there, the second option. So you have 0 equals VA plus VB, and then you made the relationship of A is equal to VB. Is there ever going to be a time where you have to know the exact relationship you have to make, I guess?
I'm trying to understand the question.
I think I know what she's saying, but I think it's just he subtracted the VB and set them equal to each other because it's equal to 0.
Okay. So say he did it the other way, would that change your system to
No, VB would still be equal to negative VA. I think there would be this Like if
Okay.
you subtracted them.
Yeah, yeah. Okay.
Okay.
Is that what you meant?
Yes, yes.
Okay. All right. Cool.
Thank you.
So no problem, no problem. And I could have made this. I could have decided that VB was equal to negative 1/3 VC if I wanted to. And maybe that actually might be something. But it was just easier to not make it 1/3, right, for the time being. And truth be told, I'm actually later on, at least in my class, I won't always use these sign convention things. This is good to know, but sometimes these sign conventions, when we go to use pulley problems in kinetics, that might sometimes just things to come. I would say that my preference is not to like hold fast to that positive and negative this way right here. Just I'm just giving you warning ahead of time, like when we, that's going to be exam 2, so we don't really care about it right now, right? But that, yeah. So that negative is just a good thing to know. Like it just makes you go, hey, when A goes up, B goes down, and vice versa. And then like I'll just write this out for the time being, just to recognize we're just going to rewrite the thing out, and might as well just make consistent there. Okay, so this first problem right here, they say they want to find the acceleration of A and acceleration of C. They told us that the acceleration of B is going to be 32.2, and we said that down was positive, so I'll leave this as positive right now. So we can find part A of this. Let me see, zoom out, and say that the acceleration of A is going to be negative 32.2 feet per second squared. When we go to answer at the very end, I think it's important to rewrite answers. So I usually give answer boxes on my exams and ask people to please put the answers in, rewrite the thing out. And that's the time when you do this, make sure you stick with only 3 to 4 sig figs. And when I give an answer to this, I would like an arrow, right? And so this one's going to be 32.2 feet per second squared, but he's going up. I know he's negative here, but remember down was positive. So we're not going to use a negative sign here. We're going to use an arrow and give a hat, because acceleration is a vector. And so that's part A. And then also down here for the acceleration of B, right here. So now we actually need to say, maybe rewrite the thing. So the acceleration of B is negative 1/3 the acceleration of, let's see, what did I do wrong? Yeah. No, I could have left it the way it was, dummy. Okay. So that should have been, no, yeah. I'm messing up. Sorry. I was right. I thought I was wrong, but I was wrong. No, I was good. Yes, I know. I got it. -3 times our 32.2, right? So whatever the hell that is right there. What's that? 96.6. That sounds right. 96.6 feet per second squared. And so is our answer for AC is 96.6 feet per second squared, also going up. And now part B of this up here, they give us, they said, oh, we want to know a velocity given a distance. So that should start to trigger us to think about the different, okay, so first off, this is a constant acceleration problem. We've established that. And so we want to go to our equation sheet, and maybe I want to pull it up. Let me pull it up, equation sheet, boom. And we are spring 22, and equation sheet, where'd you go, equation sheet? Rev 0. And it's going to come up here on my other screen, and now it does not like this. These things do not like to get dragged over from one screen to the next. Come on, wake up. Boom. Almost time for a new computer, I think. Don't tell it that. That'll be mad at me. All right, so looking at our equations right here, we maybe seem to recall that we have this relationship right there, that guy, where we know we have acceleration, position, and velocity, right? So anytime we see those ingredients together, that should be a trigger that this is the one to go with, because it's a constant acceleration. There's a change in position. We don't have to deal with time, is kind of the other way to think of it. So we go ahead and write the velocity of A squared is going to be the original velocity of A squared plus 2 times the acceleration of A times the change. I'll call it Y here, but I could have called it S if we wanted to. And personally, I would abandon the sign this convention right now. We don't worry about up, down being negative. I would do like a mental reset onto the thing, and it's starting. This is the thing we want to find. This is 0. We know that A is going up, so we'll just leave it for 32.2, and then we'll say this is 30 feet right here. So our VA, and we know that it's going to be going upwards too. That helps us. So that should be what? Oh, did I leave the 2? No, I put the 2 in there. So 30 times 32.2 times 2, and then take the square root. Yep, Alicia Garcia, she left off a sig fig. How dare she? So here it is as 4 sig figs. Oh, almost made that there. And I do know it's going up, so for my answer B, I'd say V as a, they ask for speed or velocity. See, oh, there was actually another part to part B I didn't answer. I didn't go. So what is the velocity? They said velocity, so it's got to be this right here. So velocity here is going to be 44.0 feet per second. So I got a hat to be velocity, and it's also, we also know he's going upwards, so we need to put that in there. There was a second part I forgot to ask, part B. She snuck it in there. It's my good friend Alicia. We talked together. Said, how long does it take for A to reach the pulley? Right. So now that we have this velocity and we have the acceleration, and now we want time. So we could have actually gone, if they had asked us that without like asking us this velocity, we could have done this a different way. But here, because we already have this velocity, we could say that VA is going to be VA naught plus acceleration of A times T, right? We could use that, the simple one right there, because we have that already.
Could we also use x is equal to x naught plus vt?
Yes. And we would not have had to go through this as an intermediate step. So I'll write that out too. So this is it starts from rest, 32.2, here's T. So if we divide 32.2 in there, we should get 1.365 seconds. So the second part of that should have been 1.365 seconds. What you were saying, what we could have done, and I guess I decided to go with Y. So we could go Y is equal to, like, call it YA. Let's call it A, but here's the original position plus VA original plus 1/2 acceleration of A T squared. And we're thankful now that we're starting from rest. Otherwise, we'd have to do a quadratic here. Well, we don't have to because we have that gone right there. And it depends where we decide where 0 is going to be. You have to, you can't play the game here like the original position is going to be 0, so we're going to have 30 here, and 0 plus 0 times t plus 1/2 32.2 t squared. And t better end up equaling, so we take 30, multiply it by 2, and divide by 32.2, and then take the square root. Oh, and look, we get the same thing. We better. So this was like an alternate way to do the thing if we wanted to, right? But we did it in 2 steps here. We could have done it in 1 step. But they asked both things, so. And then we could have done the other way too. It's like once we had this time, we could have gone back up in here, and with that, stuck back in there, and then found this if we wanted to. So it's a choice we made. And the last one, we want to find the velocity of c with respect to b, and I think I could fit it in here. I don't know. Yeah, maybe. I guess I could, but I could squeeze it in. But maybe it's a good modeling, as they say, the educators say. So you should model like what you want your students to do. You shouldn't be a hypocrite. Which I haven't had you and students for long enough for you to have heard every one of my rants about how I believe hypocrisy is the necessary human trait that people that gets maligned. We need hypocrisy in this world, otherwise every society will break down. But not many people believe that, but I do. Let's see. So we want to have at t is equal to 1 second. Right here, so that's going to be a pretty simple one right there. We would say that VC, right, and it's going upwards, right? We decided VC was going upwards. Is going to be VCO plus acceleration of c times t, right? So that's just going to be 0 plus r 96.6 times 1. Spoiler alert, 96.6 feet per second, and that's going up. And then we also say, well, what we wanted was b, right? So b, and now I'm going to say that it's going to, I could use the positive and negative to keep track of things, or just I'm just doing it to emphasize that it's up and down, right? So we started out at rest, and now it's going to be negative 32.2, because all of a sudden I've decided that that's down is now negative 32.2 feet per second. And I don't want to put an arrow there. I could rewrite it without, just as, once again, good modeling for students. They don't use the negative with an arrow, right? So I just take the time, rewrite the thing out just to express yourself. And then they asked for VC with respect to B. So that is VC with respect to B is VC minus VB, right? Just remember that from the definition of what that means, right? So it's just easily done, where we have 96.60 minus 32.2. And we're going to end up with I think it's 129.8, maybe something like that. Is that right? I think so. 96 point. See, I need to use my calculator for that. That's how sad that is. So just mock me. Mock me if you must. 128.8 feet per second, and it's positive. So what we would say in our answer up here for C would be VC with respect to B is 129 feet per second, and it's going upward because it's positive. See, I have a laugh button right here. I actually have 2 of them. I wasn't sure. I didn't really like this one, so I bought another one. And it was just I got really lonely over the pandemic. I had to be a remote teacher. All right. Any questions on that one? 35 minutes. I need to pick up. We need to go for now. Let's go for quality, not quantity.
There was a problem that I saw in the textbook that was a pulley relative motion problem, but it was on like an incline.
Okay.
Would you be able to do that one as well if we have time?
Sure. Let's. I have a illicitly obtained PDF of the book. Dr. Asaki gets me books. And I just dropped my ruler, so I'm looking for. There it is. It's very upsetting to drop my ruler. Doctor, if you haven't been to my office, or Dr. Asaki, he's right across the hall from me. We're like we're office buddies. Boom. And I joke that we have our own intercom system, which is to yell at each other across the hall. Which is interesting because the person I refer to sometimes that did a lot of these problems, Dr. Alicia Garcia at the Coast Guard Academy, she was also across the hall from me, and we too had a good working relationship in which we often would yell across the hall at each other. I miss her. I miss her kids. I bet her son is so big, and I bet he doesn't remember me. He loved me to death. I love Skyven. He's a sweet kid, a little rambunctious. One day, and amongst my like brick and brack, I had a so I don't see one like you're describing. There might be one here at the review problems at the end, maybe. And amongst my stuff, I didn't even think about it. I had this razor blade. He's like 4 years old, and he picks this thing up and goes, "What is this, Ted?" I'm like, "Ah!" Sorry. Maybe you had a different edition of the book. I know the one. I think I know the problem you're referring to, or
Yeah, it was like at a 15-degree angle. I think you put it on one of the suggested problems numbers. Yeah.
Okay. Where did it go? Where did it go? I must be losing it. That's okay. There you go. So that was 11/124. Why isn't it? Why didn't I see it when I went
Yes,
by?
that one.
11/124. Let me go to here and oh, you know what? So it must be down a lot further than 124. Oh, I guess. Okay, there it is. Okay. Yeah, you haven't signed this one as homework before. So let's see. Boom. I guess I could go, I'll go this over to the side and zoom it in if it'll let me. I don't like it with the little plus thing doesn't, it goes away. I'll get over it. Let's see. Make it 150. Can I get it? Can I squeeze in there? There you go. Okay. And boom. Oh, no. I want to have that in front and that over to the side. Okay. So I am drawing my little thingy here. Make a little drawing of it. So then you don't have to see nothing as I take the time to draw the thing out. But I do think it's important that you kind of like hear or see my process, right? I know it's drawn right there, and maybe I could have printed it out or whatever. I really think there's a lot of value. But I'm going to make this a little bit more angled. A little bit. I think there's value to drawing things. But then again, I'm biased because I like to draw. Not everybody enjoys drawing. Not everybody is like you, is what I've been told. Not everybody's like me. That's a good thing, right? But as I'm drawing the thing, I'm thinking, right? I'm going, oh, okay, that goes back onto there, and I go, kind of like makes me think a little bit. And let's see, this guy likes to go up, so I'm gonna make it go like that, and then Kind of wish I had made that. I'll make these parallel so it doesn't look like it's. Okay. Got a lot of stuff in there. All right, so there's a 15. That 15 is with respect to this, though. See, I'll make that. What's nice about this, you know, the see-through thing is that you could see where that line is parallel. That's one of the advantages. It's not like I'm trying to sell you on the. I just like these rules. And this one is actually the see-through. They actually wrote see-through. I don't think all the ones that I've gotten have been see-through. And this I didn't make this to scale with the 25 degrees here all that well. And this is A and this is B. And let's give us the givens here. They tell us at the instant shown, block A has a velocity of 8 inches per second. And they don't tell us what direction that is. Oh, both directed down the incline. They did. Okay. So we're going to have VA is equal to 8 inches per second. And let's say that he's just going down that way. And it's got an acceleration 6 inches per second squared, also down the incline. And okay, so now we want to find VB, I guess that's A, and B, AB. All right, so we didn't need to do anything about the relative stuff going on here. That's a I bet actually there might be another problem somewhere along there where they ask for the relative motion. That's a fair problem to ask, I think. So what's the relative motion of these two things? So let's do that after the fact. All right, so let's after we're done with this. Okay, so let me try to remember how to do this. Yeah, this is a tricky one. I think I want to make my, I know I want to make a reference from here to right there. And I'll call this SA, right? I'm just looking at these cables. I'm going, well, I know that these lengths between here are the main things that are going to change, right? And we could also make a reference to this right here, okay? And I'm gonna probably, I think so that I don't screw this up, I might be a bad man and peek and see, because I think there's a trick that's involved right here that I can't see immediately, and I'm not a fast thinker. So I know that if I sat here and I stared and I messed with it and I screwed it up a few times, I would eventually come around and go, oh, I see. But I think, let me try it and then I'll see if I'm wrong. All right, so just based on the lengths of this appears to me, I can't think of any other reason why it not. The length of the thing is going to be 2SA plus SB. And I've decided that that's plus and this is plus. And it kind of makes sense. As A is going to go down, B has to go up, right? It's really just the orientation of this that they're kind of like putting this in here to mess with your mind, I think.
So why are we ignoring the line between those two pulleys in the middle?
This guy right here?
Yeah.
Because he's never going to change, right? That pulley is never moving away from that pulley.
Okay. I see that now.
And I'm almost convinced that I'm going to be right, but by doing this, they really do kind of like make you go, they get you out of your comfort zone. And it does feel dirty, but what they've done is they've really kind of like, do you really understand what's going on, or are you just mimicking what you've seen before? So that would be my impression of what they're attempting to do. But let's see, what number did I say this one was? I said it was 124, right? Something like that.
It was 11.124, yeah.
Yeah. Okay, so what we're going to be able to find, right, when we find this guy right here, this SB, we might actually, so here was the trick, right? Here was the trick, and I think I would have run across it. I'm pretty sure I would have in a minute or two, but this is not SB. This is SB with respect to A. Right? So this right here is not the motion of B entirely. This is only the motion of B with respect to A. So we would stick that in there.
If that block wasn't there, then it would be with respect to just B. But because it's in contact with that block, it's with respect to A, correct?
Yeah, because we would want to know the absolute value of B, right? But B's absolute value of its motion, right? If A is moving, B is moving with it, right? But now they're going to move this way right here. One A is going to be moving down and B is going to be moving up. And so the motion that gets generated by this cable, right? This right here, even though we're showing A over here, is part of A. So the motion of this cable, or the length of this cable, is really dependent on the interaction between these two, not just based on the motion of B alone. So that's like the little trick right there. And I think as I started to go down here, I would have gone backwards and gone, wait a minute, I can't do that because I'm trying to find the velocity of B, right? And let's make them into vectors right here. So one thing that they've done is kind of a bastard thing. I'd also noted is they're using triangles, which is a good thing to do, but you should be able to do it without the triangles as well. So anyway, what we're able to find right here, we're able to find the magnitudes, right? These are all about the magnitudes. They're not about the directions onto the thing. But we can say that we can get the velocity, or the speed really, of this guy is going to be negative 2 times the velocity of A, or the speed of A. Same thing with this is going to be negative 2 times the acceleration of A. So we know this is negative, I'll just do it in my head, 16, right, inches per second. And this is going to be negative 12 inches per second squared. Assuming that downwards is possible. And we don't necessarily, I don't think the sign is going to help us in this pursuit. So I would actually probably just go the absolute value of that. Now, the thing that we want to do to be able to answer, and remember this is B with respect to A, we need to go that B is equal to VA plus VB with respect to A as vectors right in here. And now I have to start thinking a little bit harder here. The relative motion of, well, the motion of A right? So we could write out V of A is going to be equal to 8, and then write it's going to the left, right? We said it's coming down this way right here. 8 times the cosine of 25i plus, but that's also going down, so it's negative 8 times the sine of 25j. And the book has used triangles, but I think of triangles as being my backup, not necessarily the way that I want to solve problems. It's the way I want to like confirm my problems. It's my preference, but the book does a lot of, in its solution manual, does a lot of things with just straight triangles, and I think it's a better idea, in my opinion. While I'm here, oh, and look, when they did the acceleration, they did do it by vectors. Look at that. They did. I guess they did kind of do it both ways. Maybe I want to take this and write that this is going to be 6 cosine of 25i plus negative 6 times the sine of 25j. So 625 cosine times 5.438i, 625 sine times so negative 2.536j. These are inches. I've turned the meters into an inch, and this is inches per second squared. Okay. All right, so when it comes to the for B now, right? So we have the magnitude of B, and we know it's going upwards and to the left, and it's going to be doing 25 plus 15, which is 40, right? Did I do that right? Anybody want to give me a yes or no? 15 plus 25. I want to say, yes, you got that right, Dr. Deal. I go, thank you.
Professor, I have a quick question.
Okay.
When doing that top part of finding the vector, finding the velocity for A and the acceleration for A, you kept the 8 and 6 positive because in that direction was positive, and the -8 and -6 because it was going down in that direction, right?
Yep, exactly. Yep.
Okay, thank you.
And I'm doing the same thing for this 16 for the B, because I have this magnitude. I'm kind of ignoring this. Like maybe I should just write, this thing right there. I'm getting rid of my negative. I'm changing my mind of something I wrote previously, right? And I'm just going to write absolute values of all these things right there. Because I only want the magnitude, because I can decide what the direction is for myself. And the sign convention, it might coincidentally be the same thing, but I'm basing that negative because it's going to the left, and I'm going to take my cosine of 40 now, and then but it's going up, so now it's going to be positive 16 sine of 40 j. That's my inches per second, so 16 40 cosine time. So I'm going to get a negative 12.26, let's call it, and a 16 of 40 is sine times, and we're going to get a 10.28j. And then lastly, acceleration of B with respect to A, 12. It too, I know, is going to have to, it just inevitably has to go the opposite direction of A. And it's going up. So 1240 cosine times negative 9.193. So now, the main thing that I want to find, like I wrote that one out. I could have also written out acceleration of B. Well, I want to find the acceleration of B. So here we go. I just started writing V for some reason because I'm trying to talk and write at the same time. I can't do it. You would think that's a prerequisite to being a professor, but they never ask you if you can do that. You know what they also never do? No one ever watches me and sees if I can teach or not. I mean, not like I've actually, I voluntarily asked other professors to come in and give me feedback and during class, but no one ever requires it. Like lots of professors, nobody would ever tell whether they can teach or not. So no one would ever know that I have these. I totally lack the ability to talk and think and write at the same time. So anyway, I'm going to write out this guy right here. And so I'm going to take A first. So I got my 7.250 minus this, minus 12.26, right? And I'll have my negative 3.381 minus 10.28 J. And so 7.25 and 12.26, and we're adding them together because it's minus minus. So we get
Shouldn't we be
19.
adding since we're doing V of A plus V of B in respect to A?
You're right. I'm sorry. Yeah. What was I thinking? I wasn't. I got distracted by my little story about the things. And yeah, thank you so much. You would do well on the exam. I just would have missed a couple points. It's just a math thing. I was like, hey, it's not plus, it's not minus. You wrote it right up here, dummy, but you did dummy. I never call you guys dummy. I call myself dummy. So 3.381 and 10.28. Yeah, okay. We're in the calculator wrong. 899 J. So that's my VB. So that's going to be my answer. But I think they didn't say as much, but they want to have the magnitude and direction. And once again, I'm running out of paper. I didn't manage my paper very well, but I have more, so that's totally fine. But let's get that. So I'll go on another sheet here. So 5.010 squared and 6.899 squared and 5.01 squared and 6.899 squared plus square root. So we get 8.526. Woohoo! Same thing they got. Thank you. And then for the angle of that velocity, inverse tan of our 6.899 over 5.010, 6.899, 5.01, boom, a tan. I get 54.01 degrees. So, and that is definitely going upwards to there. And then just complete the square here. Acceleration of B, acceleration of A plus acceleration of B with respect to A, hat. So we go, A is 5.438, add in negative 9.1, that looks like a, oh, there it is, 93. Oops, and this y component of A was negative 2.536. We're adding in B, which was A with B with respect to A, which is a positive 7.713. Hewlett Packard advertising calculator for you. The one I had in college died eventually, but I liked that one better. I should try to figure out what model it was. It was the engineering model, and it had a complex notation thingy on it that was so easy because you could use it for this type of thing and to get the magnitude. So you never had to do the what do you call it? I know this calculator must have that in it, but it was like a prominent key, and I used that thing like all the time, like an incredible amount of time. So like if I were to write here, I would never have to write out this and that right there. I'd never have to calculate that because it was just a button that you just put the two numbers in there and went from, you would call this the complex, and then it would go to polar. Just jump back and forth between complex and polar. I love that thing. Never had to do this right here. I bet your TI 89, 84, whatever the hell they are, I bet they do that, right? Students seem to like that calculator. I don't know. I'm hopelessly addicted to this calculator. But they don't make the one I like anymore. I actually went to Manhattan because I went to the Merchant Marine Academy in Long Island, and we went to Manhattan often. One of the few things that was nice about the school was its proximity. And I bought my Hewlett Packard at one of those. They used to have tons and tons of those small, like almost kind of a electronics boutique kind of place right there. Like tons. So anyway, let's see. Notice it's the same angle that we had up here above, and the answers. The velocity of B is going to be equal to, where'd you go? 8.526. Let's go 3 sig figs. I like I used to insist on only 3 sig figs, and then I expanded. I tried to be a little bit more forgiving and to say 3 to 4. Like, and then yeah, oh, thanks a lot so much that nobody cares. Here you go. This guy.
Professor?
Yep.
In the first one on the page above it, right? How come you didn't put the negative 5.01 when finding the angle, since in the I direction it's negative 5.010, and you
I got you. Okay, so this is my method of doing it. I mean, if the negative works for you, that's okay. But I just take a look and see that one's negative and that one's positive, so I know what quadrant it's going to be in. So when I go down to like report the answer, that's when I decide to give the thing. Some calculators, I think if I put that negative in there, it will report like maybe the complement of this, I think. But the trouble with a tangent is that you could have a negative and a negative on top of each other, and it won't know whether it's negative or not. So I ignore the signs when I do the angles, and then I just find the angle with the rise over run, and then base the quadrant when I go to report it on knowing what quadrant it's in.
Okay. So I did both. I did both for the angles, and the first one just came out negative. It's the same. I was just wondering.
Okay, no, it's a fair question and more information than you want. But this problem comes up actually in Excel if you want to try, instead of if you were working on some kind of problem and you wanted to automate it, but because you're going to do it over and over again, and you needed to use the inverse tangent so that you could find the angle of the thing. You run across that problem that if both of them were negative, it'll return the same angle as if both of them are positive, and you wouldn't have the correct quadrant. So there's actually in Excel, there's a thing called A tan 2, right? Where where we usually have A tan to get that, that's essentially what we're doing here, right? But there's A tan 2, and it's a little weird because you have to put you call the two things out, the X and the Y right there. And then then it knows when it's negative and it's not negative and gives you the correct quadrant if you're going to automate the thing. But I'm going to avoid automating it and just make sure that I'm describing the correct quadrant right here.
This is
But
going
now
to be
you know of the existence of ATAN2. When I discovered it, made my life better because I do stuff in another class where we want to try to make spreadsheets to solve the problems, and the arctangent has that annoying thing.
Before you move on, this is probably going to be a stupid question, but can you just
It
explain?
couldn't possibly be. I argue with you. It's not a stupid question. I haven't heard the question yet, but it's not.
So when you were finding your velocity A components with cosine and sine, can you just show me how you got those trig components? Because I'm trying to draw it out and I just am drawing it wrong.
Okay. All right, no problem. I just want to first off, before I forget, I was going to point out that this is what the solution manual did. Well, first off, I want to point out I got the same answer. Whee! So satisfying. But they went ahead. They did the velocity one right here. They didn't do it the same way as me. They went ahead and did a triangle, and then they did right here the law of cosines to get the magnitude, and then they did the law of sines to figure out the angle. That's a good skill to have, but it's not something. Just because of time constraints, I don't like push it hard here, but I do try to emphasize, hey, be able to draw the triangle. But let me try to answer your question, right? Wish I had another color pen. I do have another color pen somewhere. No, yes, no, I do not. I'm a liar. All right. All this stuff up here, and I don't have another color pen. Exactly. These things must be really old. Oh, here's one. All right, so one of these must work. All right. So you were asking right here. So let's say, okay, so first off, let's go to this one up here. So I wanted to get the velocity of A, and I know he's down this way right there, right? So he's kind of, I know that's 25 degrees, so I know that has to be 25 degrees, right? This is the 25 degrees right here, so I knew that one had to be. So I saw that in the X direction, that's going to be like the adjacent component of that. Some people would not have had to draw that, but I kind of did that in my head.
Okay.
So it's
no, I get it.
Your question is totally valid because I was doing something in my head, but mentally I drew that thing out. Does that make sense?
Yes, it does. Drawing it out, I was drawing it in the wrong direction, so that's why I was confused. So
Okay.
Thank you.
I'll tell you, there's a whole lot of benefit in the course to these little tiny things that like are different from what the main I'll even write out here are our learning objectives, right? And they're all about the dynamic stuff, but there's these little things that kind of like pesky little stuff for trying to get you want to sort out, and a whole lot of the course is organizing your thoughts and sometimes is relearning some things that you hadn't done and remembering when you're going to use certain things that are from maybe even years past, right? So sometimes you have some weird algebra thing that like, yeah, I don't even ever remember ever doing that, but then you did, and you get to use. So there you go. All right, so where are we going with this? We're in the problem. We did a lot of pulley stuff, so we might have probably branch out to other topics here. I think I had. Can we do a polar coordinates? That was just asked. Okay, yeah, Dylan. Yes, absolutely. So we have a lot of ones to choose from. One I was thinking that would help you with your homework is this guy right here. All right, so he is similar in our class to the homework problem number 2. Is that okay right here? And then I might adapt to this one, and I'll show you a couple things that might help us generally. Like I would never ask a problem that would have as many steps as I think I'm going to make this one more complicated than it currently is, just to be as a demonstration of maybe using a coordinate transformation, which I don't think is maybe necessary. Yeah, we don't really have to do a coordinate transformation because it's 180 degrees. So I might want to find another opportunity to do that, but I will use this to find a trait. Like I might want to have the radius of curvature of this. Yeah, I think I'll try that. We'll see. All right, so what's the best way to do this one? I think I'll cancel out of that. I'll go up. Let me do up. And why don't we do the up? I'll do the side, but not up. Right. Go over to there. Yeah, it's kind of hard to see that, isn't it? All right, well, let me do my best. Let me bring this over here. Where'd you go, Catman Joe? I'm gonna remember to do a coordinate transformation soon. That's what we gotta do. Okay. So I got this little doohickey thingy. I'm not even sure what it does. Oh, it's got like, oh, I see. It's like a almost oval looking thing. And it's got silver thing inside. It's got a little ball inside there. I don't know what the purpose of this thing is. I'm sure it's got some kind of meaningful thing. I'll put it over there. Didn't do a great drawing. Not my best work. Oh, you can't even see it. But this thingy has an equation where the radius 0.5 is a function of theta, and it's in feet. And we're measuring theta counterclockwise, coming this way. Right here, so they're showing it. And we also, this thing is spinning with the theta dot and a theta double dot. And the radius of it is measured right here. We are. Are they the same? And it looks to me like this is a funny little kind of shape. All right, so the track matches it for a little while, but then it comes off. And this right here is actually that funny little shape right there. And it says here, if the ball's velocity in that position is 4 feet per second, and its acceleration is 30 feet per second squared at 180 degrees, which is shown, we want to find theta dot and theta double dot. That's a good problem. All right. Anything else I know? So, and by the way, this right here, they said this acceleration right here, I think they should have made it clear that it's probably going to be that acceleration, the tangential acceleration, not the full acceleration, right? But let me take a peek as we go down the thing, because I think it's moving around in this direction. This piece is also going to have a normal component to its acceleration. So I think they meant that thing's going to be AT right there, right? This AT. But let's check them out as we go through. So one of the first things I want to do here, if I can, if it's going to let me. Come on, I'll get rid of this. Maybe. How come it will not let me focus? Oh, it did it. Just what I was trying to. All right. So, anytime we're dealing with polar, a good mindset is to the variables of interest, right? The VOI. Look for the VOI. Now, some of the VOIs, these are our goals. So let's stick with this guy first as our VOI. And I'm looking at something. Okay, wow. We were kind of lucky in this location. I see they cheated a little bit. All right. I started to think like, how the hell are you going to do that? Okay. So we'll take the R dot of this function. And we wanted a time derivative of something that doesn't have time in it. When we have to do that, right? So we want to have, if we want to take the derivative of R when it's a function of theta, what we do is we take the derivative of with respect to theta and then just multiply it by d theta dt, right? So when we say the product rule, use the chain rule. I meant the chain rule. Product rule, other thing. This is the chain rule. When I say use the chain rule, even when I say use the product rule, I might have accidentally called the chain rule the product rule. Sometimes I might have meant the chain rule, but the chain rule here is like a chain. You know that those two are going to cancel out. So we can take the derivative of this with respect to theta. That's easy enough. But then all we need to do is must multiply it by this, which we happen to know is also known as theta dot. So we take derivative of the above, which is going to be the derivative of cosine, right? The one goes away, and the derivative of cosine is a negative sign. So all we're going to get is a 0.5 times the sine of theta for that part of it. But that's just with respect to theta. We also need to multiply it by theta dot. Now, we want to have the second derivative of it, but noteworthy, this varies with time and this varies with time. So now we have to use the product rule on both parts right here. So we have to do, first we'll take the derivative of this first part, which is going to be 0.5 times the cosine.
I have a quick question. Does that theta dot represent the dr d theta that you had written up there? Or not, sorry, the d theta dt, that's what I meant.
Yep, yes, it does.
Okay, gotcha. Thanks.
It might have fallen off the edge of the camera right here.
Oh, I see it
But I
now.
kind of
Okay.
like that thing became that.
Thank you.
You're welcome. So we did take the derivative of this times the original, and then we do the original times the derivative of that, which is theta double dot. Now we have, we're working towards our variable interest. We'd like to get the magnitudes of these. So we have this function up here, and we're told that it's at 180 degrees. So we put in our 180 degrees into there, and we're going to find that R is going to be the boring, that turns into 0 right there, right? So it's just 0.5. And R dot, when you go to put in the 180 degrees, let's see.
Are you doing this in degrees or radians?
Well, right now I'm doing it into degrees, but it's a good idea. You could convert this into radians and make sure you calculate. You got to be really careful with your calculator that it's in radians. If you see a theta by itself somewhere, I would say use radians for it. But right here, I could just think of it as the cosine of 180 degrees, right? I could also say it's the cosine of pi if I want to instead, because pi is equal to 180 degrees. I'm looking at this here. It's like, is the sine of 180 degrees should be 0, right? I'm trying to think.
Shouldn't
Is it
R
equal
be
to
1?
Yeah, shouldn't it?
I got 0.
Because we have 0.5 times 1 minus cosine of 180, and if cosine 180 is -1, then that's 1.5 times 2.
I totally agree with you. 1 second here. Why the y? I'm thinking. It doesn't make sense. The original thing doesn't make sense that it would look like the way that it does if that function is correct. Right? It starts off over here. So the cosine of 180 degrees should be equal to 1. So it should be 1 minus 1 times 0.5.
Cosine of
Y.
180 is -1.
Oh, 180 is -1.
Yeah.
Ah. So now should equal to 1.
Yes.
You're right.
Yes.
I'm not a smart man, but I know what love is. That was a Forrest Gump quote, by the way. I'm not a smart man, but I know what love is. All right, good, cool. Thank you. Sorry. 180 in here, that makes that 0. That's good because we didn't know theta dot. That would have messed us all up. We didn't know theta dot, but just it works out the right way. I'm glad you guys are here to keep me in line. All right, so oh, wait, I made a mistake here. When we were doing the derivative of this right here, and we took the derivative of the first part here, we also needed that we took the derivative with respect to theta. We needed to have another theta dot in there, right? Does that make sense? I totally forgot to do that.
Can you explain that one more time? Or like try to rewrite
Okay.
it so I see it?
I see it yet. All right, so when we went from here to here, recall, we had to use this chain rule. We had to say, well, we can't take the derivative of this with respect to time because it's a function of theta. But if we use this right here, this is like a way to get around that. So we took the derivative of it with respect to theta, and then we multiplied on here. Now when we go to do the second time, where we're going to take first, we're going to do the product rule, where we're taking the derivative of this part. This is also just a function of theta. So when we go to take the derivative of just that part right there, sure, we get cosine of theta, but that's just taking the derivative with respect to theta. We also need to do that thing again where we had d theta dt. So it needed another theta dot. It already had a theta dot from the original one. We're doing a product rule. So we had to have an additional theta dot, and I just totally spaced and forgot to put them in there. Does that make sense?
Yes.
A little bit? Okay. All right, so when we put the 180 in here, that's just going to make that into, -1, right? Am I remembering the cosine of 180 is -1, right?
Yeah.
Yes.
So we have 0.5, and here's our theta dot squared. Okay. And this right here, 180 is going to be 0, sine of 180. So that one goes away. So right here it becomes our variables of interest. We're still kind of stuck a little bit with some of the things that we wanted to get. Oh, I see. All right. So the way I read the problem was a little bit wrong. When they told us this up here, they meant that right there. Well, this didn't affect anything because we would have recognized that up above, but they were saying the magnitude of the acceleration, right? I didn't read it that way when I was reading the problem, so I would have missed out points on here. But like they said, if the ball's velocity is this, and they should have said speed, and if it's acceleration magnitude, they should have said was this right here. I assumed because of this the way right there. You know what you do when you assume. So anyway, when we go to find the velocity of this, remember that for polar we have r dot er plus r theta dot e theta. So if we want to find the magnitude of this, we would take r dot squared plus r theta dot squared.
Dr. Deal, why
But
did you ignore the plus 0.5 sign theta dot double dot for our double dot?
up here,
Yes, why
because we
did
were doing
you?
it at 180 degrees
Oh,
and
okay.
the
Thank you.
sine of 180. Yeah. And then, but we notice in here that we have 0 for this, right? And for our, oops, then we go plus, we have 1, and we have theta dot, and that's all squared. And we know that that's going to be equal to 4. They told us. So based on this right here, we could do this and square that, but then we'd end up taking it times 1. So we end up finding that theta dot is going to be 4 radians per second based on this relationship right in there. So we're able to get part of it. And then for the acceleration, well, let me write out the full acceleration equation. R double dot minus r theta dot squared er plus r theta double dot plus 2 r dot theta dot, which you'll remember this is the Coriolis, right, kind of thing, and this is kind of similar, and often in circular motion this would be centrifugal right here, that guy. And what we were given was that the magnitude right here, so that's going to be r double dot minus r theta dot squared plus r theta dot plus 2 r dot theta dot squared, and that was equal to 30. So r double dot is negative 0.5 theta dot squared. Well, look at that right there. Okay, well that's negative r, what, I'll put it in there, negative 0.5. Did I get that right? Times r, which we know is 1. Theta dot squared minus r, 1, theta dot squared. Oh, and by the way, what we could have done, I'm sorry. Why am I doing that? There's no reason. We have 4 up here. We could put 4 in there. Plus, and we're going to have 1 right there. Theta double dot, that's the last thing we're trying to find, plus 2 r dot, which we know is 0. So this other one didn't really matter, but we could put 4 in there for that, and then squared equals 30. All right, so this appears to be, yeah, we could find that, square that, bring him over to the other side. And so that's going to subtract that from 30, and that would end up being the theta double dot. All right, so I could find that. Go 30, square it, and we're going to have 8 and 16 together, right? 8 plus 16 should be 24. and we'll square it, but it's gonna be over to the other side, so I'm gonna subtract it and then square root it. Do we get 1 point? We get 18? Yeah, we get theta double dot is equal to 18 radians per second squared. And okay, so something I might want to know based on this, let me think about this. All right, so if I was going to continue with this problem, well, first off, the velocity, this speed right here is entirely in this direction right there, right? So that's fine. But this acceleration has two different parts to it. So let's investigate that just a little bit further to give us a little bit. So we can now, I could use that to find the radius of curvature of the part at this time. So I can find this acceleration here. I'm going to plug it into this equation right here. So I can have r double dot was negative 0.5, and it's 4 squared, minus, right, so that's going to be r theta dot squared, 1, 4 squared, right there. So that's going to be ER. And if I'm correct, I believe that's going to be a negative 24, right? Because that's negative 16, and that's going to be negative 8, so that'd be negative 24, plus, we'll say that this is going to be, or this is 1 times our 18, and like we said already, this is going to be 2 times 0 times 4, so it didn't matter, E theta. And so this is just 18. So our acceleration here is a negative 24 ER plus an 18 E theta, feet per second squared. Well, from the arrangement right here, if, looking at that thing, let me redraw the thing out there. Here's my E theta and here's my ER, right? But if I look at the particle right here, tangential is this direction, ET, and this is EN, coming towards the center of curvature, right? So if we were going to be a little nutsy and say, well, I want to do a coordinate transformation between these two, I would take my, well, I guess I got with this one right here. I take my ER and my E theta, and then I would take my EN and, nope, ET, excuse me, and my EN. So I don't even need to do a coordinate transformation thing. I could just know that my ER is equal to negative EN, and my E theta was equal to my ET, that they're aligned with each other in our coordinate transformation. So what we could rewrite that acceleration as being 18 ET plus 24 EN. Does that make sense for this situation here?
I have a question.
Okay.
I don't know if you covered it earlier or not, but I just couldn't remember. So the theta is in 180 degrees, but then it also says that theta is supposed to be in radians. Did we have to convert it or no?
We didn't have to convert the radians because we never had to write it out anywhere. we only had to put it inside of a cosine and a sine, right?
Yeah.
We only had to put it in there. So we could have had our calculator in radians mode if that was the case. And we always have to be careful when we're doing a problem where we might, for a little while have to put it in radians and then make sure you put it back later on. But we didn't have any thetas that were just kind of hanging out by themselves. That can happen, by the way, in some types of problems where you might have to actually multiply something by a theta, but it didn't happen in this case.
Okay.
So the last thing I want to point out is that from this, we also know that the normal acceleration is v squared over r, or the radius of curvature, which is not the same thing, not always the same thing. This is not always the same thing as r. And in this case, it's not, because if you look at this shape right here, this thing has a radius that's probably like a lot bigger than just the radius right here, because it's not a circle, right? A circle would have this radius right here. It might be the same, but let's check it out anyway. So what we would say is that the velocity, which we know to be 4 squared divided by the radius of curvature, is going to be equal to 24. So the radius of curvature, we would multiply, we would say that would be, right, be 16 divided by 24. So 0.6667. That's interesting. That's not expected. I thought it would be bigger. No, I guess I could see. All right. So if we take a look at the diagram that they have here, right? If I can move the thing over to the other side, it won't let me do it. Right. So here is the book this came out of. You can kind of see, yeah, maybe taking a peek at this. Yeah, I can see that. Okay. It's going to be a circle that's smaller than this radius right now, instantaneously. Does that make sense? What I'm trying to explain is that there's a radius of curvature to the thing, because it has a tangential component, and we know the tangent, tangent and a normal component. We know the normal component must point towards the center of curvature, so it's got to point inwardly. So it's going to be equal to this amount, and we're able to find the radius of curvature from knowing that this has to be true. Even though we're using polar coordinates for this stuff, the path is established, so the path coordinates will still hold out.
I have a question.
So, okay, go ahead.
How do we know that E theta is pointing down?
Okay, let me think, because it always points to the left, counterclockwise. It's going counterclockwise from where R is, right? So you have an R going this way, it goes to the left onto the thing.
Gotcha, that makes sense. Thank you.
You're welcome.
Can you go back to when we solved for our theta double dot? I just got a little confused with how you got negative 0.5.
Okay. Because cosine of 180 is -1.
Oh, yes, it is. Okay.
Yeah, I agree with you, because I totally spaced on that when I got up to here on that first part. When I got to right here, I'm like, how did I? Because I wrote down 0.5. I was like, I thought of 100. I thought cosine of 180 was 0. I was just jumped ahead. I should just read the damn thing. That's what I should do. Let's do one with a coordinate transformation. What do you say? Nothing too crazy, but let's try to find in my problems here. one that might lend itself to a coordinate transformation or a projectile motion problem. I'll let you guys decide. Projectile motion or coordinate transformation. Or we could do a coordinate one that require a projectile motion that requires a coordinate transformation. Like we do the skier, and we could ask the question, what is the radius of curvature of his when he lands? Ooh, that might be hard. But might be worth trying to do it. It would not be a good exam question. It would be evil. How about this guy right here? Which is, I haven't done this problem before. It's moving in this circle. Well, you know the radius of curvature of that, if that thing is a circular arc. Oh, here you go. Nozzle discharges a stream of water in the direction shown with an initial velocity of 24. Determine the radius of curvature of the stream as it leaves the nozzle or at the maximum height. By the way, part B is a trick. It's a trick problem. Well, not necessarily. No, it is kind of a trick. It's easier than you would think. You could do part B like really quickly. It's like easy. And well, you kind of can do it. Yeah, you kind of can do both of these, right? There's not really a projectile motion problem. Boy, that's a little deceptive here. Now let's do this problem. Why not? I like it. It's a little deceptive. Not a lot deceptive, but just a little deceptive. Is that okay, or does somebody have like something else they would rather do? You can totally veto me. I don't mind. I don't hear any bloops. Actually, I kind of wonder if there's anybody else left. Anybody here? Oh yeah, we got lots of people here. Oh, somebody just said, oh, Miles said the coordinate transformation. Okay, Miles wins. Woohoo! All right, where we go here? No, that's not the one. This one. All right, you can barely read that. Yeah, so the thing is coming out at shooting out here at 55 degrees. And for some reason, this thing looks like that. I don't know what that is. Okay. And the initial velocity is going to be 24 meters per second. And find a radius of curvature at the nozzle, and B, why am I drawing it that way? It's a terrible row. At the peak, or at the zenith, we could call it the zenith, right? So this is like a really easy problem once you see the thing, right?
Isn't the angle supposed to be on the other side? I'm not sure if that makes a difference.
Oh, did it? Let me see. Let me double check. It may. Oh, I'm sure it does. Oh, yeah, you're right. Thank you. It does make a difference. It'll make a 20-degree difference.
Can you explain why the angle's on the other side?
Because that's the way they gave it. I don't know. Some maniac decided to reference vertical, and I'm just not used to referencing vertical. You see what I'm saying right there?
Yeah. Okay.
Why would they do that? I don't know. But anyway, so what is that? That makes it this 35 right here, right? Math, sure. 80 and then 5 plus 5, 90 degrees. Got it. Okay. So the velocity in the oh, I don't need that part yet. I was going to do part B first. I'll just do part A. So what you could say is right here, the initial we could have this as ET and EN. Right? Because this is the orientation of this as it starts out, right? Velocity is always tangent to the path. The initial velocity is at that angle right here. So we would put that right in here. So if I was going to do a coordinate transformation array, I'm going to use 35 right here. So I'm going to use that angle instead of the other angle right there. But that would be right here and right here and right there. I call that theta. So here's my I and J and E tangent and E theta. And by the way, this is going to seem like overkill, but it is, you know, working through and practicing our coordinate transformation. We could do it like in one step, but let's go ahead and use the tools we have available. So I and T are related to each other by the cosine of theta, assuming theta is 35 right there. We're using that guy. And he's going to be sine, positive sine, right? Because he's going tangent compared to J. They're both upwards together. I wrote down, looks like I wrote down theta, and that's supposed to be an N. And he's also going to be positive, but he's the opposite from the angle. So he's a sine. And then you just know by your pattern that that was going to be a negative cosine, but we could also confirm that here is the angle right there of the theta, and it's cosine. Yep, and it's definitely in the negative J direction, that EN. So what we would like to do is find the acceleration in the normal direction. If we could find the acceleration in the normal direction, we can use this property right here to find the radius of curvature. In other words, the clue that we have to do all of this is the fact that they asked for the radius of curvature. So, well, what do I know about the radius of curvature? Well, there is an equation. It's not in Beer-Johnston, but they are in some books. I did provide it in class, but I haven't done an example with it, and you don't necessarily need it for the radius of curvature. So really the only thing we have available to us and on our equation sheet is that the radius of curvature is related to the acceleration in the normal direction. So how would I find the acceleration in the normal direction here?
You can use the components based off the fact that we know our V initial.
Okay.
You could first find the velocity. No, it's like, never mind.
That's okay. It's all right. I just want you to I just want you to think about it, and then when I tell you, you're going to slap yourself in the head. All right.
Because you're given an initial velocity, so you need to have a final velocity.
Is it just gravity?
Gotcha.
Oh.
I heard it. All right. Somebody else think what he just said. What did he say?
Gravity?
Good job, Dylan.
That's projectile motion.
Yeah, it is projectile motion, and it's just gravity. But what am I going to do with gravity now? Maybe I could write it this way. The acceleration is we were told these are meters, right? We told us meters per second. I think it was 24 meters per second. All right, so just negative 9.81 J.
Could you convert it into your transformation coordinates?
Exactly. Yep. So what we could do is we could turn this into tangent and normal. right? And then we will have this component, and we know already the initial velocity. So we'll be able to find the radius of curvature at the beginning. So all we have to do is, and this is in the J, so we're going to come down this way. So we'll say the acceleration is going to be negative 9.81 times the sine 35 ET plus negative 9.81 times the negative cosine of 35 En so 9.81 35 sine times, so it's a negative 5.627 ET plus 9.81 35 cosine times, and that's negative, so it's positive 8.036 En meters per second squared. So what we know is that that's going to be An. So we have 8.036 is going to be equal to the speed, initial speed 24 squared. So the radius of curvature is just going to be 24 squared. So it's going to be 71.68 meters. And that was part A. Part B is kind of easy. Because what do we know about the situation at the peak right here?
Velocity 0.
Is the velocity 0?
Isn't acceleration 0? Turns around.
No, the acceleration is still 9.81. This is the direction it's moving, right? When it gets to the peak. So what's the speed at the top? You kind of answer. You said the word, so I told you that you were wrong when you said it was 0. You were like, what you said was incorrect, but what you were thinking was partially correct. Maybe if I say that the right way, right?
One
What's the
component
speed
is
in the
0.
y? What the speed in the y direction is 0, right? At the peak, it's like pausing at the top, right? It hasn't. It's not neither going. It doesn't have a velocity up or down here at the peak, right? It was going up. It was going up, and then it stops here. Then it's going to start having the velocity go down right here. But it still has a velocity in the x direction. And remember, it's a constant velocity in the x direction, right? So the x velocity in the beginning is the x velocity here, which is the x velocity everywhere. So the speed at that point right there is just going to be the velocity in the x direction, the initial one, right? Which is going to be equal to the initial velocity times the cosine of that original angle. So 24 times the cosine of 35. So 19.66 meters per second is the speed / velocity at the peak. What's the acceleration?
Still should be negative 9.81.
Yeah.
Yep, it's just 9.81, and it's just a line. It's entirely right there, right? So you have, once again, so you'll say that it's 9.81 is going to be equal to, we just said 19.66 squared, and the radius of curvature. So the radius of curvature right there is, square that and divide by 9.81. And so now we have a 39.40 meters. So it was kind of a coordinate transformation problem. It was also a projectile motion problem, but not necessarily in the way that you would think, right? We didn't have to necessarily solve for the landing spot or the initial velocity or whatever. But it's still projectile motion because it makes you kind of think through what's taking place in a projectile.
I have a question.
Yep.
So the reason why our normal acceleration is just 9.81 is because we only have the y direction, correct? Whereas at the beginning we had an x and a y direction for the normal acceleration.
Yep.
Okay. Thank you.
And by the way, this, if you were to look this up in the book, they would do this like in a one step, like everything that I drew like right up here would be, but it would make it, I think, a little just too, and you'll just go, oh, okay, yeah, okay, oh, I just take the cosine of the thing, right? That's all I really had to do was take the cosine. Well, I guess in their case, they would have used the 55 degrees, probably because I was just stubborn and didn't like using the vertical as the reference. But yeah, you would just see it in one step, and it'd be kind of like, oh, okay, that's just information. But here, I think, by drawing this out right here is kind of the chain of thought that you would go through to be able to establish and figure that out on your own, hopefully, right? But now it's also just something that, you've seen two examples of it right here in these two parts. So anytime that you're looking for the radius of curvature, you could what the big idea is just be on the lookout for an and how you can find it, what the normal acceleration is going to be. Notably, though, what we did find out when we had it in this position, this initial position right here, this is the rate of change of its speed, right? Like its initial speed is 24 meters per second coming out of this thing right here, but it's decreasing, right? That the magnitude of its speed is decreasing until it gets to right here. Then it's going to start increasing the speed along the line that it's traveling. But at this initial time right here, that tangential acceleration is its change in speed. So its change in speed is negative 5.627 meters per second squared. So if someone was trying to draw that out from you, and I'm not saying I would do that, but if a professor was someone writing an exam, they would say, what is the change in speed, right? And that's what they would mean. That was the thing that they would be looking for, and their expectation would be, well, maybe that you would do a coordinate transformation, or that you would know that you would need to take, in my case, the sine of 55 times the acceleration of gravity. I could keep on going. Does anybody want to have like another one? Or we're at our 2-hour mark here. So hopefully the storm holds off because I have a gig tonight. Exciting. I'm playing music. Use my new amplifier. Make loud noises. All right, the solutions to the practice problems are going to be posted at I think I have it set for 8 o'clock Sunday night. I really trying to encourage you to work through problems trying to solve them on your own. But of course, you could always ask me. I'm available to meet or to answer emails, whichever is more useful to you.
Thank you, Professor.
You're welcome.
Thank you, Professor.
Good luck at
You're
your
welcome.
gig. Hopefully you can go.
Yeah. Well, I think I'll be fine. I just don't know how many people will show up because the Connecticut weathermen get everybody up in a frenzy.
Thank you. Have a good one.
Deal. Can I ask you a question about the homework?
Sure.
So for problem